So this is a screenshot from the textbook talking about roots and radicals. So the symbol that most people are familiar with is the square root symbol. And so that's what that looks like. That is the symbol. So we call this the square root symbol. But the general symbol for that is also called a radical. So its other name is a radical. So when we are talking about simplifying radicals, we're talking about simplifying whatever is inside that thing. So whatever is under the root symbol or under the radical inside it, that's what we're trying to simplify that thing and try to make whatever's underneath it easier to work with. So that's sort of the goal when we start working with variables and all that sort of stuff. But first, we just want to make sure that we're all on the same page with numbers and how you're working with the square root symbol and radicals, and you know what happens when you have a number up in the upper left corner. So to compare, if there is like a 3 up there, that is called a cubed root symbol. So that is the cubed root. So that 3 is telling us that that's the cubed root. That kind of tells you what root it is. If it's something to the 4th, we call it the 4th root. So we only have special numbers for like a 2 or a 3, and then it's 4th, 5th, 6th, and so on. So that's the cubed root symbol. Those are the two special, more common ones that you will see. And what it means when you have these symbols is that you're basically undoing an exponent. So these undo an exponent. So I'm going to just scroll down here. So if you see the square root of 4, and you're saying, okay, what is this? Paul says it's the inverse of the exponent. It's not exactly the inverse. When we talk about inverses in math, we have a very specific definition for those. So we wouldn't call it the inverse because that's something different. That's a term that we use specifically when we're dealing with functions and equations. So this is just like a property kind of thing. But it is undoing the exponent, because you're basically saying the square root is saying, okay, what squared gives me 4? That's the other way we can translate it. As you have some unknown here, what squared equals 4? So this unknown thing that we're looking for, that would be underneath the exponent of 2. That square root says that we're looking for something with an exponent of 2. So 2 squared gives us 4. So that means the square root of 4 is equal to 2. So that's sort of what the square root does. It's basically asking you what's underneath the exponent if you were to square something. Similarly, if we had a cubed root of 27 and we wanted to know what does that equal, that would be equivalent as if you have something that you don't know and it's cubed and it equals 27. So you're asking what number cubed gives me 27. Now a lot of people don't really know their cubes very well. Usually people only really know their squares, but 3 cubed actually gives you 27, because that would be, whoops, stole my highlighter. Make this orange. So that'd be 3 cubed, because 3 cubed is equal to 3 times 3 times 3. So you're multiplying 3 times. That's what that exponent says. The exponent is how many times are you multiplying these numbers together. And 3 times 3 is 9. So that's equal to 9 times 3, which gives us 27. So that means the cubed root of 27 is equal to 3. Now what I recommend that you guys do is you make sure you have a calculator to calculate these things. Most calculators have a square root button. A lot of calculators also allow you to do cube roots. And I think mine, the symbol, it has like a little X instead of a 3. And every calculator is sort of different on how you enter it in, so you'd have to look at your manual or look online. But most calculators can do square roots and cube roots. And so it's undoing the exponent. Now going back to these generalizations, we have to be very careful about what our root is. So generally we work with square roots, but basically if you have anything that's an even root, you can only have positive numbers underneath. So if you have a square root, or you could have something that's like a 4th root, you can have something that's a 6th root, any even root. So 2, 4, and 6 are even numbers, must have positives inside. Positive numbers inside the radical. So you need to have something positive inside the thing if it's even. This is not the case with exponents. This is specific to radicals. So Paul asked, is this the case with exponents? No. With exponents, you can have negatives with an exponent. That's completely fine. But with radicals, you can't. So not when it's even, at least. And that is because if I was to ask you what the square root of -4 was, that is the same thing as asking what squared gives me -4. There is no way to square a number and get a negative, because if you're squaring, you're multiplying two things by itself. A negative times a negative is always going to be a positive, and a positive times a positive is always going to be positive. So since the exponent there means you're using the same number, the only two possibilities always get you a positive out. So that's why you can't have a negative, because there's actually no solution. And so a situation like this, we would say that there is no real solution. There is not a real number that will make that true. So with evens, we need to have something positive under the radical symbol in order to come up with a solution. It's completely okay to have a negative outside. I could have a negative in front. So I could have a negative and then the square root of 4. And that's completely fine, because I can take the square root of 4, and that would give me -2 as my answer. So then if negative is outside, that's fine. It just can't be inside when it's an even root. Now, on the other hand, when you're looking at odds, it doesn't matter. So if you have a cubed root, you can have a 5th root, you could have a 7th root, anything with an odd number there. So an odd root. These can be positive or negative inside. It doesn't matter. So we can have positive or negative. Let me make that a little neater. Inside the radical. And again, that radical is basically the part that's underneath there that I'm highlighting. So if I take an example, and let's say have the cubed root of negative 27. And so that would be equivalent to saying, what? We have some unknown thing cubed equals negative 27. Now, to get a negative answer when you're multiplying things together, you have to have an odd number of negative signs, because a negative times negative gives you a positive. But if you have a third number there that's also negative, you now have a positive times a negative, and that gets you a negative. So for something like this, negative 3 gives you negative 27, negative 3 cubed. Because negative 3 times negative 3 times negative 3, when you multiply those first two negative 3's together, the negative times negative is a positive, so we get 3 times 3, so we get a positive 9. And then we have times another negative 3, and that gives you a negative 27. So for something that's an odd root, like this cubed root of negative 27, you can get an answer, and your answer would be in the negative version. So if there's a negative inside the root, your answer will be negative when it comes out. That's the general rule there. If I have a positive and it's an odd root, then it's going to be a positive answer coming out. So this sign, those signs need to match for odd roots, basically. What's underneath for an odd root is going to be the same sign when you take the root. So that, going back to, and now my picture doesn't want to show up. There it goes. So that's essentially what this in our textbook is saying. It's just saying the rule about if it's even. It's giving the rule about if it's odd. And then the last one here is 0. So this just says that if you're taking any radical of 0, your answer is always going to be 0. So square root of 0 is 0. Cubed root of 0 is 0. It doesn't matter what kind of radical you're taking, you're going to get 0 out. So that's what that last rule is saying. So this is the basic rules about radicals and at least how to evaluate simple ones. Do you guys have any questions so far? Okay. Well, the next thing that I wanted to cover, I'm going to paste this in too. These are the properties of radicals. So again, this is coming from the textbook. And I kind of wanted to go over each of these properties to kind of explain how they work and what it means. I know there's these examples here, but if you're not really seeing it explained and you're just looking at it, it may not make sense. So I wanted to kind of go over each of these. So I'm going to start with property 1. And I'm going to write this bigger because it is really small here. So property 1, yeah, you're welcome, Paul. I know, like, the picture is really, really tiny, so I want to make sure that everybody can read it. So property 1 is saying that you have something with an exponent inside your radical, and what it's saying is that you can flip those. You can kind of flip the order, and you'll get the same answer. So if you have something with an exponent inside, you can kind of move it on the outside and do the radical first, and then do the exponent. So they have an example with 8. Let's see, let me try to find a good example. let's say I have a fourth root of 81. So how this rule works, or where it comes into handy, is, okay, you're looking at 81. Right now it's not matching this property, but I know that 9 times 9 is 81. And 9 times 9 is 9 squared. So I can rewrite this as 9 squared. So what this property is saying is that what I could do is, instead of having that square on the inside, I could take that fourth root of 9 and then put the square on the outside. So that's all that property is saying, is that you can kind of rearrange the roots and the radicals. In this case, the fourth root of 9 is, it's not a nice number, so it wouldn't necessarily be beneficial for us to do this, but it's just giving you an idea that you can actually rearrange those if you wanted. The example problem that they give is that they have a cubed root of 8 squared. And so if you wanted to find the cubed root of 8 squared, I'll do it two ways. Let me do this in a different color. And I'll start in the middle. So we have cubed root of 8 squared. So there is one way to do it, and then there is one way using the property. So one way you could do it is to square 8, which would be 8 times 8, which is 64. Then you would want to take the cubed root of 64. That is, like I said, people don't really know their cubed roots. But one that, and I only know this because I teach this all the time, but 4 times 4 times 4 actually equals 64. So 4 cubed is 64. So I can rewrite this as the cubed root of 4 cubed. Now, this rule of exponents, and I didn't actually, we're actually going to take a look at this property 5, because I think that should be the first property here. So property 5, just move here, because I think this is one of the easiest properties, is if you have some radical, and actually the way they've written it is different. They have their thing on the outside. Let's look at property 6, because that's basically, it's essentially the same thing. It's just putting the exponent on the inside of the radical or versus outside of the radical. But basically, if you have like the root, like if it's a square root and then you have something squared, or if it's a cubed root and you have something cubed, if those match, the exponent and the root match, those essentially cancel out and you're left with what's underneath. They have this rule on number 6 that it has to be the absolute value, and that's just because we can't have negatives if it's even. So that's the only thing. But basically, as long as it's a positive, if it's an even root, they just cancel out. So that's property 6. So going back to here where I'm showing property 1, the nice thing about property 6 is if we have a cubed root and then our exponent is cubed, those just cancel out. It kind of removes the whole symbol and the exponent, and you're just left with what is underneath, which is 4. So that's one way to do the problem, and just write a little note there. Going from there, that is property 6. Now the example that, this example using property 1, So if we go back, property 1 is you can interchange the exponent and kind of put it on the outside instead of the inside. So using that property would mean that you have the cubed root of 8 and then you square. So instead of having the square inside the 8, you'd kind of have it on the outside. So you can use your calculator to figure out the cubed root of 8, but you can also try to write it as exponents. And I always try to do it that way so that you can see that these things cancel out. Plus, it makes it easier when you're working with variables. So 8 is actually 2 cubed, because 2 times 2 times 2 will give you 8. So I can rewrite this. We've got the cubed root of 2 cubed. And then I still have that exponent of 2 outside there. So once again, I can use that property 6, because I have a cubed root and then an exponent of 3 inside there, and those cancel out. So this would give me 2 inside the parentheses, and then I have the exponent. So that step that I just did, that's again that property 6, where the root and the exponent cancel out. Then, for this step, we have 2 squared, so that gives us 4. So doing it this way is actually one extra step, but it's an alternate way to do the problem using this property 1, where you can interchange your exponents, whether they're on the inside or the outside. So that's what property 1 says. So I should clarify that going from here to here was using that property 1. And this is one of the reasons why a lot of people struggle with radicals, because there are multiple ways to do the problems. So there's not really one set way that you can solve and get the answer. You can get the answer using different properties or going in different orders. You'll get to the same spot, but they may take a different number of steps. And I know a lot of people get frustrated with that because they think that math has one right answer. And there is one answer here, but there's just multiple ways that you can get there. And it's all about what works for your brain, what is your brain looking at, which property makes most sense to you. There's no right or wrong way to get the answer when you do properties, when you're looking at these properties and you're trying to simplify things. So that's property 1. The next one I'm going to look at here is property 2. And this was when you're multiplying radicals, because this is another very handy thing. So property 2, let's say, let me make sure I'm using the same letters. Okay, so they have something like A underneath the radical, and then B underneath the radical. If you have 2 things that are multiplied together, they have the same root, so they're both square roots, or maybe they're both cubed roots. You can multiply those together and combine them into one radical. So this property is used a lot when we're trying to simplify radicals. Usually we're going from something where they're multiplied and then we're going to the left. So we usually have something on the right end and we're going to the left. Sometimes we go from the left to the right. Let's see the example that they give us. Well, that's a very simple example. Let's say I have, this is actually a very common example here. A lot of times we're multiplying things together where it's identical, like square root of 2 times square root of 2. We will actually do that quite a bit. Things like that. So this property says that you can put those underneath the square root and do 2 times 2. So that would be this step here is using property 2. Now if we want to simplify, we can write that as 2 squared. Now a square root, we don't write the 2, but we essentially have a 2 outside there. When we have a square root, we just assume that it's a 2. So that means that we have a square root and then we have something squared. So those cancel out. And so when those cancel out, you're just left with the 2 left over. It cancels out the radical symbol, it cancels out those exponents. That was that property 6. So going from here to here, we used property 6. So that's one of the things that's really nice with radicals is if you're multiplying 2 square roots together, they essentially cancel out and you're left with what's underneath. Now it's a little different when you have cubed roots. In order for a cubed root to cancel, you'd actually have to multiply 3 of them together because they don't cancel out the same way. But this is a property that we use a lot when we're trying to simplify. We're basically trying to cancel out things inside a radical symbol so that we can pull numbers outside of it and we don't have the radical symbol anymore. So that's property 2, and property 3 is very similar. Property 3 says essentially that you can do the same thing if you have fractions. So if instead of multiplying these together, I have them as a fraction, you can combine them and make a fraction inside. So again, usually we're going from something with a fraction inside and we're pulling it out and we're doing the other direction. But you can also take 2 separate fractions and combine them. I actually have, let's see, this is a good example. This is actually one that I had kind of pulled out. So I'm going to take a cubed root, and I'm actually going to go from the right way to the left. So I'm going to take something where it's already in one fraction inside my cubed root. So I can use this property 3 and separate this out so that I have the cubed root of 64 and then the cubed root of 125. So going from my first step to the second, that is that property 3. We're just going in the other direction. Now what I'm going to do is, again, I want to try to cancel out these radical symbols. And your goal is, if you have a cubed root, you want to try to write things with exponents of 3 because the cubed root will cancel out exponents of 3. So as I mentioned before with 64, that is 4 cubed. So I'm going to rewrite 64 as 4 cubed. Now on the bottom we have 125. So 125 actually is 5 cubed. So I'm rewriting these with exponents of 3 because I want to be able to cancel those out. Because the cubed root will cancel out anything that has an exponent of 3. So once I match those, the root to the exponent, I can just remove those completely. And then that gives me an answer of 4/5. And once again, going from here to here, this is that property 6. That's a very useful property. The fact that you can cancel out your radical symbol if the exponent on the inside matches. Let's see, we don't really work with number 4 very often. Number 5 is essentially number 6, just in a different order. It's just using property 1. So those are like the 3 basic, well, 4 most important rules, because you got property 1, property 2, property 3, and that property 6. Those are the most important rules that you need to know when working with radicals. And so now I'm going to do an example. Well, actually, before I move on and do an example, I should ask, do you guys have any questions so far? Okay, you guys are welcome to ask questions. What if b has an exponent attached that is different than the cubed root? That is an excellent question. So I'll do this one in green just to. So let's say, okay, so we have a cubed root. Yes. So Chris asked, what if b has an exponent attached that is different than the cubed root? So what if we go back to that 64 over, and then let's do, we'll do 81. So we're going to simplify this. We're going to first split it up using that property 3. And then we're going to try to write these as exponents. So again, we know that cubed root of 64 is 4 cubed. Now that 81, so our goal is to write it so that it has a power of 3. Here's the thing with the 81. 81 is equal to 9 squared. So that does not have an exponent that was a 3. So if I wrote it like that, I would not be able to simplify the bottom. Oops. Because my exponents don't match. That 3 and the 2, they don't match. I can't simplify those. So I could cancel out on the top, but my bottom would remain the same. Now what we can do with 9 squared is we want to try to get it down to prime numbers. So 9 is not a prime number. Our goal when we're trying to simplify radicals is to get to prime numbers. So prime numbers. Let me do this in black. Prime numbers are only divisible by themselves and 1. So a simple list of prime numbers are 2, 3, 5, 7, 11, 13, 17. So none of these numbers have something we can divide into it. 9 I can divide by 3, so it's not a prime number. Our goal is try to get these to prime numbers because it makes it a lot easier to simplify, and we can actually simplify further than just looking at 9 squared. So what I usually do is what's called prime factorization. So prime factorization is where you're just trying to make things down as low as it goes as far as prime numbers. And I do this with a factor tree. So I start with my number. So we'd start with our 81. And I just split it up into branches. And I'm just looking at what numbers multiply to 81. Well, 9 times 9 multiplies to 81. So I'm going to just branch that out. And then I say, okay, are the ends of my branches prime numbers? If they're not, then I branch them out again. 9 is 3 times 3. So I can branch out both 9s by having 3 times 3. 3 is a prime number. So when I've hit a prime number, I circle it. So that's sort of like the end of my tree. And what this means is my starting number 81, I split up these into things that are multiplied together, is really equal to 3 times 3 times 3 times 3. So how does this connect to this problem that I'm doing where we have this 9 squared and we can't simplify because it's a cubed root? Well, 81, instead of writing it as 9 squared, I can write it as this multiplication of 3's. And 3 of the 3's I can write as 3 cubed, because there's 3 of them together. And now I have something that I can take the cubed root that has an exponent of 3. So going back up, I have this 4, and instead of writing this 81 squared, or this 9 squared, we did this prime factorization. I'm going to write this as 3 cubed times 3. Now, I'm going back to use this property 2, where I'm going to go from the right to the left, where you have two things multiplied, and then you can actually, if you go from right to left, you can split them up. So we're going to use property 2, by making it the cubed root of 3 cubed times, and then another cubed root of 3. So going from here to here, that was using that property 2. I'm undoing that multiplication. Now I have something where my root and my exponent match, so those can cancel out. So that is property 6. I can use property 6, and then that gives me 3, and then I have this cubed root of 3 left over. And unfortunately, I can't do anything with that. So you would just kind of have to leave it there, because we can't simplify that any further. There's no way to rewrite 3 so that it has an exponent of 3, because there's nothing like that. It just doesn't work. So, Chris, this is a long answer to your question, but your question is, what if that b, that denominator, had an exponent that was attached that was different from the cubed root? Well, if it has something different from the cubed root, then you try to rewrite it so that it does have a cubed root in some way, and then you can simplify. And if you can't simplify, then you just leave it as it is. So does that answer your question fully? Okay. Yeah, I'm going to do more examples. And actually, this particular one right here, we would then have to do an extra step called rationalizing the denominator, but I'm not going to go over that. Next step would be rationalizing the denominator. You guys won't really need to know that too much. That's not going to be something you're going to have to do often, so I'm not going to go too. I'm not going to cover that here. I'm trying to cover the stuff that you guys really need to know, especially for the assignment, and especially like when we start doing the quadratic formula in week 3. You're going to have to work with radicals. We work with radicals in week 3 when we're solving radical equations. So I'm just trying to get you guys the basic skills that you need so that when we get to week 3, you'll have, you know, what you need. So the rationalizing the denominator, I'm not worrying about too much. And I think another example would be very helpful. Let's see if I can find. Okay, I'm going to do another example. And this is just going to be another cubed root, just because a lot of people are not very good with cubed roots. So They're kind of easier to work with, or better to work with, so you guys can get more practice. And I'm going to throw in a variable there just to show you that the rules work with variables and with numbers. So we have the cube root of 16x cubed. So 16x cubed, that whole thing is underneath the cube root. And we want to simplify this. We want to kind of make it smaller. Now, one thing that we can do immediately is notice that on our x, we have an exponent of 3, and then we're taking a cube root. So just with the numbers, just that property 6, we can do the same thing with variables. And when you do that, when that cube root of 3 and that 3 cancels out, we basically put it in first. But I'm going to show this in 2 steps just to make this clear. So let's actually first separate the numbers from the variables. So this is that property 2. We're just going in reverse, where we have 2 things multiplied together. We have 16 and then we have x cubed, so those are multiplied together, so we can separate those out. Now I can use that property 6 directly to cancel out my cubed root and my exponent of 3. So that would give me my cubed root is 16 times x, or we'll usually write it as x times the cubed root of 16. We'll just kind of put that in front. So that's using property 6. Now we want to try to simplify that 16. So I'm going to go do that prime factorization, the factor tree that I did for 81. We're going to also do one for 16 because the goal is we want to try to rewrite that so we have something with an exponent of 3 so we can cancel it out. We want to try to cancel out that radical as much as possible. So I have 16. So what are 2 numbers that multiply to 16? You're always looking for pairs of numbers that multiply together. So you can just type it into the chat box. Give me 2 numbers that multiply to 16. And they do not have to be the same numbers if that's not what you think of first. 2 times 8, 4 times 4. Both of those work and will get you the same answer in the end. I'm going to do 2 times 8 just to show you a different kind of factor tree, but you'll get the same result if you did 4 times 4. So 2 is a prime number. I can't split 2 up, so I'm going to circle that. But I can split up 8. So then I say, okay, what are 2 numbers that multiply to 8? So it could be 2 times 4, 4 times 2. The order does not matter. And again, 2 is a prime number, so I'm going to circle that. Then I'm going to split up my 4, which is 2 times 2. And those are prime numbers. So 16, if I take all of my circled numbers together, I have 4 2's multiplied together. And I want to get them in sets of 3 because we're looking at a cubed root. So everything wants to be a set of 3. So I can group those 3 together and write this as 2 cubed times 2. So I'm going to go back up to my x times the cubed root of 16 that I have here. And I'm going to write this x is on the outside. And then I have my cubed root of 2 cubed times 2. So I've just taken that prime factorization, and then I've just tried to rewrite it so that I have things that have exponents of 3 so that I can cancel it out with my radical. So now I want to split up my radical again using that property 2. So I'm just going to work down here. Normally I write things a lot neater than I am right here. I try to organize it a little better. And I'm just going to split up that multiplication so that I have 2 separate radicals. And then I can cancel those out for at least one of them there. That cubed root of 2 cubed, that cancels. That's that property 6 again. So, whoops, I thought I was in the blue. Cancel that out. There we go. So we're going to use property 6. And when we do that, we continue working down, we have our x. And everything here is multiplied, so I'm going to just put a dot there. And then I get a 2 because the cubed root and the 2 cubed cancel out. And then I have a 3 and a 2. And I can't simplify that cubed root of 2 because 2 is prime and it doesn't have an exponent on it. And then normally when we write this, we'll put the 2 and the x together. We'll put our number in front. And then we'll have this remaining cubed root. We can't simplify it any further, but we simplified it more than we did. The goal of simplifying a radical is to try to get everything outside, as much as possible from outside, or outside from the inside. You want to remove things from the inside and get them outside if possible. Chris, did that give you some additional help with what happens if your exponent doesn't match with the cubed root? Okay. This particular problem is actually very similar to the one on the assignment where you have a 5th root. So for that one, you want to make things grouped in 5s because it has a 5 on the outside of the radical symbol. So that tells you what to group things. So if we're on the homework one, it's the 5th root, you want to group them in 5s. If it's a square root, you're going to group them in 2s. You're going to pair them up so that you can simplify it. Are there other questions that people have? My goal, in addition to answering any questions that you guys had, was to basically get you through enough of radicals so that you'd be able to do that problem on the assignment. So I've pretty much given you everything that you need to do that problem on the assignment, I believe, unless there's additional questions that I might have missed or things that you need some additional clarification on. You're welcome, David. Paul, actually exactly what we did is simplifying an expression. Okay, and then Lacey, okay, you're confused about the homework having x to the 6, not x to the 5. Okay, so I will address Lacey's question first. So our homework problem, we have the 5th root of 64x to the 6th. So for the 64 part, do a factor tree. So everything that I did in orange where I split it up, you're going to do that with the 64. So it's just like I did with the 16 and the 81. With the x to the 6th, this part, so x to the 6th is equal to x times x times x times x times x times x. It means that there's 6 of them multiplied together. So we can group these just like with the numbers. So we want these to group in 5s because it's a 5th root. So you would use x to the 5th times x. So when you're on that homework, we have that 5th root of 64x to the 6th. I can split that up to the 5th root of 64 times the 5th root of x to the 6th. I'm going to leave the 5th root of 64 for you guys to do, but then I can split this up as x to the 5th times x. So I'm going to leave you guys the number part because that's the easier part. But I've got my 5th root of x to the 5th, and then my 5th root of x. So you'll be able to cancel that part out. So I have my 5th root of 64 times, and then that middle part just leaves me an x. And then I have my 5th root of x. So this part you guys will need to simplify further. I will not do the whole problem for you, but I've done essentially half of it for you. Yes, so it works basically the same with the numbers. It's just you have letters instead. I mean, that's the thing with variables. They have the same rules as numbers. So once you kind of think about it that way, then it's not so scary. Okay, so Lacey, that answers your question about that homework. And then Paul, you were asking about simplifying an expression. So do you mean specifically about simplifying any expression or radical expressions? Because what I've done here is considered simplifying an expression. Where you can simplify a polynomial within an expression. Okay. Are you referring to, move my folder off. Let me see. I'm assuming you're referring to one of the problems. You can simplify a polynomial within an expression allowed. Are you referring to one of the homework problems, or are you referring to a problem in a book? I just want to make sure that I understand your question before I attempt to answer it. Okay, and instructional. Okay. Do you have the what it looked like? Oh, if it's allowed. Yeah, I mean, yeah, there are multiple ways to simplify. Okay, so your question is, can you simplify a polynomial within an expression? Is that allowed? And the answer is yes. So when we're simplifying polynomials, you're generally trying to add like terms. So if you have like addition going on and you have the same exponents and the same variables, you can add those together. If you have polynomials inside a radical, then you would need to make sure that you have one thing inside the radical. It needs to be kind of grouped together under one power in order to simplify that. There's lots of different ways that you can do it. It's a matter of what it looks like. So if you want to like maybe email me or a screenshot of that video, which one you're talking about, so I know exactly the type of problem, that would help me answer your question better, because it really depends on what it looks like, what else is going on with the polynomial. You can always simplify, but it's a matter of how you simplify depends on what else is going on. I know it's not a clear answer, but yeah, if you can find the example and email me, then I can give you a much better example or a much better answer. Does anybody have any other questions? And if I'm not able to answer it, of course, I will ask for more information. Well, I'll stop sharing my screen. If you guys don't have further questions, what I'm going to do is once the video processes of like the recording and everything like that, I'm going to make sure that I email that out to you guys, if not tonight, maybe tomorrow morning. And I'm also going to include the file that I was writing on. So I was writing on OneNote and I had this like little whiteboard thing. I can actually save that as a PDF. And so I'm going to save that as a PDF, and then I'm going to email that out, or at least put it in the same area as the video, so that you have access to this So that way if you want, if you want to review notes or if you want to say, okay, what was she writing down, you'll have copies of that so that you can do that. The whole number's in front of a square root. Okay, we can talk about that. Let me share my screen again. Okay, so Lacey says that she's confused about whole numbers in front of a square root. So I'm going to, let's see, just give an example here. Let's work with a square root this time. Let's say we have a 3 in front of the square root. And if it's not a small number, if it's a big number in front, then it's not a cubed root. So you have to make sure there's a difference. That is not the same as putting the 3 up there. So you have to pay attention to the size of the number. But if we have 3 and then the square root of, let's say, 16x, we'll do 16x. That's simple enough. Okay, and you have that number is assumed to be multiplied. So if you were to simplify something like this, we're going to use that same property where we're going to split up what's underneath the radical symbol. And we're just assuming everything is multiplication. So that's going to be 3 times the square root of 16 times the square root of x. Now when you have things that are square roots, you want things to have exponents of 2. Actually, I'm going to make sure that I write. This is property 2. This is good for your notes too, so that like when you're writing notes, you write what rule that allowed you to do that. Okay, so for square roots, I want to have exponents of 2. So I have my 3. 16 is equal to 4 squared. And then I have my times the square root of x. So this square root, it doesn't have a number, but we assume it's 2. And then that 2, those cancel out. And so that allows us to write this as 3 times 4 times the square root of x. So that's using property 6. That the square root and the square, they cancel out. So what happens is if you have that number in front and then you have another number, you just multiply those together. So now it's 3 times 4. So you just multiply and that gives you 12. And then, oops, I don't know why I wrote a 3. That is an x. Then you have your square root of x. And then we can't do anything with that square root of x because it doesn't have an exponent. So we can't get rid of the square root. And so the x just kind of stays underneath there. But those numbers that are in front, you multiply those together. Does that help answer your question or clear up your confusion, Lacey? Helps a little. Okay. I could do another example. Let's say we have negative 2 times the square root of 3. I'll do one with addition just to kind of also have those numbers in front to kind of show you what happens there. Homework question 2E. Let me actually pull that up so that I can make sure that I'm 2E. Yes, okay, the numbers in front. Okay, so actually, I will do something similar. I'm going to be making up. These are not going to be the same. You can see they're different numbers, but we will do this. We'll go through the steps. So the steps will be roughly the same. We just have different numbers here. And so this is similar to 2E. What is front of the, oh, sorry. That is a plus. Oh, now that's a terrible 4. Plus 4x. And then we have a minus 4x. So when you have something like this and they're multiplied together, you want to use FOIL. So we're going to go through the FOIL process. And FOIL, you have the F, which stands for first. So you're multiplying these first two things together, the 2 square root of 3 times the 2 square root of 3. So I'm just going to literally write that out before we start trying to multiply those things. Then the O of FOIL stands for the outside. So you're multiplying this 2 square root of 3 times what's on the outside, the negative 4x. So that's 2 times the square root of 3 times negative 4x. The I for FOIL that stands for the inside. So that would be the 4x times the 2 square root of 3. And then the L stands for the last terms, the 4x times the negative 4x. So we've got the first, outside, inside, last. So when we simplify this, group your things together. So you can rearrange multiplication. You can rearrange the order of things. So like for the 2 square root of 3 times the 2 square root of 3, oops, I can rewrite that. I can put the 2's together. So I can do 2 times 2 together, and then I can do the square root of 3 times the square root of 3 together. So when you're multiplying things together, you can rearrange the order to make it easier on you. I can do the same thing with the outside part, the O. I can put the 2 times my negative 4 together, and then I can just put my square root of 3 and my x together if I want. And then I'm going to do the same thing on the I. I can put the 4 times the 2 together, and then I can group the x and the square root of 3 together. And then on the last term, I can group the 4 times the negative 4, and then the x times the x. This will help you simplify. So going from the left, I have 2 times 2, so that's 4. Now my square root of 3 times the square root of 3, I can combine those into one square root. Now I'm going to the next part. 2 times negative 4. That is a negative sign, so that's a negative 8. And then you usually put the x in front, and then you put your radical in the back, just because it's a little easier to read. So I'm going to just rearrange the x in the square root of 3. Now the next one, 4 times 2 is 8. And then I have x, square root of 3. And then 4 times negative 4, so that's negative 16. And then x times x is x squared. So now that I've done that row, I'm going to go underneath, and I'm going to look again on the left. I have 4, and then the square root of 3 times 3. So 3 times 3 is 3 squared. So I'm going to combine that as 3 squared. Now this middle part, these are like terms. They're like terms because they both have x, and the x has no exponent. And when you have like terms, they have to have the same radical part. So they have to have the same thing like a square root, or they need to both have cube roots. and it has to be the same thing underneath. So they both have an x, they both have a square root of 3. That's what makes them like terms. So when they're like terms, you add the numbers together. So -8 plus 8 gives us 0. So these cancel out. We get 0, so that part disappears altogether. And then I'm left with this minus 16x squared. So now going back to my left, I have a square root and then my 2 there. So those cancel out. That's that properties where those cancel out. So this would be end up being 4 times 3. And then I have my minus 16x squared. That comes from this part here. I'm just pulling over. And so then my last step is to do 4 times 3, which is 12. So I get 12 minus 16x squared. And so that would be my answer, because the 12 doesn't have an x squared, so I can't combine that with something that has x squared. So since I can't combine those, I have to leave those as they are. So that's how you would work out the problem 2e. It has different numbers, but the steps are going to be very, very similar. And you will find that the middle parts are going to cancel out on that 2e. So you're going to end up with something that looks similar, just with different numbers. Does that help you, Lacey? So helpful. Good. Okay, so Paul, you asked, you canceled out the O and I in FOIL, but what about the negative? Ah, Lacey, and you can remember FOIL. Okay, so Paul, are you asking about the negative in front of the 8x squared root of 3, or are you asking about the negative in front of the 16x squared? Which negative are you asking about? The -8, okay. Because that's a -8, that's why it canceled out. Because a -8 plus 8, those add to 0. If that was not a negative, then they would not have canceled out. But that's why we were allowed to cancel them out, because they're basically the same number, opposite signs. That's the only reason those canceled out. What other questions do you guys have? What does FOIL mean? So, FOIL stands for first, outside, inside, last. It's a way to remember how to multiply two things by two things. So we use it when we have two sets of parentheses, and you have two things and two things. You might have pluses for both of them. You might have a minus for in between, but there's either a plus or a minus symbol, and then there's something on either side. So the first is multiplying the first term in each set of parentheses together. That's when we say first, that's what we mean. We multiply the first term in each parenthesis. When we say, oh, for outside, we're multiplying the two outside things together. So that's the outside. That's the first. The inside means the two inside things together. So you're multiplying those together. And then the last means you're multiplying the last thing in each set of parentheses. So it's a way to remember everything that you need to multiply together. Because if you have two things times two things, you should get four things out. And so FOIL is a way to remember to get all of those four things. You're welcome. What other questions do you guys have? What about trinomials? Oh, Paul, are you asking about multiplying trinomials? Or are you asking about factoring trinomials? Okay, multiplying out. So, I don't use FOIL when I multiply trinomials because they get messy. I'm going to just make something up. So let's say we have 2x squared minus 3x plus 4. Make that actually look like a plus. Times x squared plus 5x. That look like a 5. 5x minus 7. So here we have 3 things that we're multiplying. And so we're going to get 9 things out because 3 times 3 gives us 9. That's a lot. So I do what is called it's called a table method. And what I do is I take the first trinomial and I write that going across, 2x squared, and I leave some space. And if it has a minus, then I write it as a negative, otherwise I'll leave off the sign. And then I go vertically with the second one. X squared, 5x, and then a negative 7. So I create a table. And you end up having 9 boxes that you need to fill in. So this helps me remember and make sure that I have everything, because 3 times 3 I should have 9. So what I do is I multiply row times column. So I just work the first row and I multiply by each number or each thing in the column, and then I move to the next row. So x squared times 2x squared. So that would be a 1 times 2, which is just 2. And then you add the exponents. X squared times x squared, you add those, you get x to the 4th. So then I move to the next column, same row, x squared times negative 3x. So I'm going to have a negative 3, and then the x adds 1 to my x squared, so I end up with x cubed. Then I go to the next column, x squared times 4, so that is 4x squared. Once I've filled in a row, I go to the next row, and then I repeat the process, doing row times column. So I would have 5x times 2x squared. So 5 times 2 is 10, and then an x times an x squared, you're adding another x, you get x cubed. Next column, I have 5x times negative 3x. So 5 times negative 3 is negative 15. X times x is x squared. Then my last column, I have 5x times 4. 5 times 4 is 20, and then I have an x. Then I move on to my last row. So I have a negative 7 there. Doesn't look like a very good 7. That's a 7. Negative 7 times 2x squared. So I have a negative 7 times 2, so that's negative 14. And then I have an x squared. Then my next column, negative 7 times negative 3x. So negative 7 times negative 3 is a positive 21. And then I have an x. And then I have negative 7 times 4, which is negative 28. And then once I fill that in, I know I've done all the multiplication. It's just a matter of adding things together. And what's really nice is that the columns, they align, or the diagonals kind of align together with all the like terms. So these all line up. And so when I write it out, so I start with my upper left corner, 2x to the 4th. And then I'll kind of zigzag. So then I'll have minus 3x cubed plus 10x cubed. And then I'll go back up to the top right, and I have 4x squared. Then I'll work my way down the diagonal, minus 15x squared. minus 14x squared. So that's the blue diagonal. Then I'll do the pink diagonal, plus 20x plus 21x, and then minus 28. And then you're going to add all of your like terms together. So I'm going to simplify. First, the 2x to the fourth doesn't have anything to add it to. But I have negative 3x cubed plus 10x cubed. So I can do negative 3 plus 10, which is 7. So that's plus 7x cubed. So when you add them, the exponents stay the same. Then my blue diagonal, I have 4x squared minus 15x squared minus 14x squared. So 4 minus 14 would be negative 10 minus 15. So that's going to be a negative 25. So I got a negative 25x squared. I'm practicing my mental math here, trying to do it in my head. But I usually, for something like that, I check myself, especially when I'm dealing with negatives. I don't always trust my brain when it comes to negatives. Then I have my pink, so 20x plus 21x, so that is 41x. And then I'm left with my minus 28. And then that is your final answer, because now you don't have anything else that matches. Nothing else matches with an x and then with the same exponent. It is a nice trick. I think it's so much easier than, like, FOIL is great when you only have 2 things because it's not too bad. But when you have 3 things, if you try to do arrows, you're going to get lost. So anything that has 3 things or higher, I make a chart. And actually, you could do the same thing even with 2 things. So if you don't like FOIL, you can do this table with using FOIL instead. So you can just do 2 things times 2 things. So I think it's so much easier. This is how I do anything that's really big, which I have had to do. When I was in grad school, we were multiplying things that had like 6 things times 6 things. And it's like there's no way I was doing that without a chart. It was way too big. What other questions do you guys have for me? You guys are a fount of questions, which is great because that's what I'm here for. Yeah, I'll stop sharing again unless you guys have more questions. I might have to split this video up in multiple videos because I don't know if anybody's going to want to sit here watching an hour and a half long video. It might have to be like, here's the radical portion, here's the non-radical portion, or something like that. Okay. You guys are welcome. Thank you so much for coming and asking questions. I'm going to stop the recording at this point.